Hi everyone, welcome back to Calculus 2 by Example. Today we're going to start the unit or the section on sequences and series. Recall that for us at this level we're going to think of a sequence as an infinitely long list and a series as an infinitely long summation. So let's look at some examples. This is going to be an example of a convergent sequence. So this sequence has an explicit definition, and it's that a sub n is 1 plus negative 1/2 to the nth power. So if n is 0, that's 1 plus 1, which is 2. If n is 1, that's 1 minus a half, which is a half. If n is 2, that's 1 plus a quarter, which is 1 1/4. And we can see both numerically and graphically that the values we get for a sub n are approaching 1. Okay? So each time we increase the value of n, we get an output value, that's a little closer to 1. All right. And so graphically, if we graph each of those values, our little points are converging to 1. And if we actually evaluate the limit as n goes to infinity of a sub n, well, 1 is a constant, so it doesn't change as n changes. And because the absolute value of negative 1/2 is less than 1, as n goes to infinity, this piece of the limit will become 0, so that we're just left with the 1. So that's an example of a convergent sequence. And it's infinite, it goes on forever. It never actually reaches 1, but eventually it will get arbitrarily close to 1. And so that's why the limit is 1. Okay. Let's look at a bounded divergent sequence. Okay, so here is our sequence definition. Again, we're working with an explicit definition. And we have negative 1 to the n power, and then we have negative 1 to the n plus 1 divided by n plus 1. If n is 0, this will give us 0. If n is 1, that means I have negative 1 plus 1 over 1/2, and so I get negative 1/2. If n is 2, that's 1 minus 1/3. Okay, so that's 2/3. If n is 3, I get negative 3/4. And we can see that the values keep bouncing back and forth, but they're getting further and further apart from one another. When the input values are odd, I'm getting values closer and closer to negative 1. And when the input values, the values of n, are even, I get values closer and closer to positive 1. And so we keep bouncing back and forth like that, with the even values getting closer to 1 and the odd values getting closer to negative 1. And so this limit does not exist. If we take the limit as n goes to infinity of this sequence, the limit doesn't exist because some of the values are getting close to 1, other values are getting close to negative 1. What we can say is that the subsuite sequence with just even input values approaches 1, and the subsequence with odd input values approaches negative 1. But overall, we say that the sequence is divergent, or that the sequence fails to converge, because there's not a single limit. There's not a single value that these numbers are getting closer and closer to. All right, one more example of looking at a sequence. Okay, this will be an example of an unbounded divergent sequence, and we have a very simple explicit definition for this sequence. It's c sub n is 2 to the n. So if n is 0, that's 2 to the 0, which is 1. If n is 1, that's just 2, then 4, then 8, then 16, then 32. So the values are starting to climb more and more quickly. 64, 128, 256. So as we move along, we start with relatively slow growth, but that growth rate expands quickly. And so these values for the sequence are following the function f of x equals 2 to the x, which is an exponential function. And so here we don't have a finite limit for this sequence, so that we say this sequence is divergent. It doesn't converge to a finite value. because if we take the limit of the sequence, if we take the limit of 2 to the n as n goes to infinity, we get infinity. Okay, so that's 3 examples of sequences. In our next video, we're going to talk about series, which are infinite summations.